Now we're starting the unit on multi-qubit gates within the circuit model. In classical information, controlled operations are operations where the state of one bit influences the operation performed on the state of another classical bit. There are 5 notable multi-bit classical gates: the AND gate, the OR gate, the XOR gate, the NAND gate, and the NOR gate. The AND gate looks like this and has a truth table 1, 2, 3, 1, 2, 3, 0, 1, 0, 1, 0, 0, 1, 1. And the output of the AND gate is only equal to 1 when both of its inputs are 1. So we get 0, 0, 0, 1. The OR gate is a gate that, so this will be 4. This is the gate whose output is 1 when one of the inputs is 1 or 2 of the inputs are 1. So we get 0, 1, 1, 1. The XOR gate, which we call 5, is the gate that's equal to 1 when only one of the 2 inputs is 1. So here we go. 0, 1, 1, 0. The NAND gate is the inverse of the AND gate. So we get 6, 7, 6, 7, 1, 1, 1, 0. And the NOR gate is the inverse of the OR gate, which is 1, 0, 0, 0. So these classical truth tables describe the types of 2-bit operations in digital logic. Controlled operations are also possible on quantum bits. When a gate has 2 inputs, they are known as 2-qubit gates. And when a gate has 2 or more inputs, we call them multi-qubit gates. A collection of qubits with only single qubit gates is not sufficient to make a useful quantum computer. This is a very important statement because it tells us that we need multi-qubit gates in order to take advantage of the power of quantum computing. In other words, the multi-qubit gates are necessary to implement useful quantum algorithms where you can get an advantage over a classical computer. The prototype controlled operation in quantum computing is the controlled NOT gate, or C0 gate. This is a quantum gate with 2 inputs. The first input is a control qubit C, and the second input is a target qubit T. The action of the C0 gate on a register containing the control qubit and target qubit is relatively simple. If the control bit is 0, the target qubit is unchanged. If the control bit is 1, the target qubit has an X gate, or a NOT gate, applied to it. This can be summarized by the following mapping, that C tensor T maps to C tensor a bit, which is the exclusive OR of T and C. Because if the control bit is 0, T XOR 0 is equal to T. So T XOR 0 is equal to T, and T XOR 1 is equal to the inverse of T. The matrix representation of C0 to 1, where the 2 qubit is the control qubit and qubit 1 is the target qubit, is the following matrix. So just remember that unless I specify, I always am going to be telling you matrices in the basis 0, 0, 0, 1, 1, 0, and 1, 1. Or in other words, we'll always be working in something called the computational basis. Which is 0, 1. So of course, this operator is acting on a tensor product vector space of 2 qubits. We can also define the CNOT gate in terms of I and X, which are 2 by 2 matrices. So let's look at this. What this statement simply means is that this is the identity matrix, this is the X matrix, this is the 0 matrix, and this is the 0 matrix. So we can check if this makes sense. If we operate C0 to 1 on a vector 1, 1, then we get 1, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 0, 0, 1, and this is equal to 0, 0, 1, 0. So this is equal to the state 1, 0. So here, qubit 2 is the control qubit, and qubit 1 is the target qubit. So we see, because the control bit is 1, the target qubit gets flipped. The control qubit stays the same in the operation, but the target qubit changes. In the Dirac notation, we can write this simply as the outer product of 0, 0 and 0, 0 plus 0, 1 and 0, 1 plus 1, 0, 1, 1 plus 1, 1, 1, 0. So this entry here is here. This one is this one. This one is this one. Excuse me. This one is this one. And this one is this one. That's the mapping that we learned in our previous section on quantum information and quantum mechanics 2. This technique to go from multi-qubit matrix representation of operators to multi-qubit bracket representation of linear operators. Now, a more general and very important gate we often see in quantum algorithms is the controlled U gate. In general, it can have one control qubit and n target qubits. The action of the controlled U gate is as follows. If the control bit is 0, the target qubits are unchanged. If the control bit is 1, the unitary U that we have to specify is applied to the target qubit. A compact way to represent this is as follows. The controlled unitary gate takes the tensor product of C and T and turns it into the tensor product of C and U to the power of C on T. Now this is working for C being an element of the computational basis, of course. The CZ gate is another important gate. It is, in fact, the gate that you get whose operation is defined by the following. If the control bit is 0, the target qubit is unchanged. And if the control qubit is 1, we apply a Z gate to the target qubit. The matrix representation of the CZ21 gate, where qubit 2, so let's say we have Q2, Q1. Here is the target, and here's the control qubit. The matrix representation of this is an identity gate for when the control qubit is 0, and the Z gate for when the control qubit is 1. Again, in this basis. This, of course, has the following more compact representation. In Dirac notation, the CZ gate is the same as the identity gate, except for we have a -1 on the outer product of 1, 1, and 1, 1. The last element here. Summary of the simple multi-qubit operations is that we have 3 very common 2-qubit or multi-qubit gates. Well, 2 of them are 2-qubit, and 1 could either be a 2-qubit or a multi-qubit gate. These are the controlled NOT, a 2-qubit gate, the control Z, another 2-qubit gate, and a controlled U, which can be either a 2-qubit or a multi-qubit gate. There are other possible multi-qubit operations, such as the swap gate, or the square root of swap. So square root of swap is often denoted like this. And when you square it, it's equal to swap.